Good morning, everyone, and thank you very much for joining us today. It's a pleasure for me to open this morning the final conference for the Fatigue4Light project. And today we have a very important topic that our consortium would like to share with you regarding the knowledge that we've developed for opening, let's say, the path for electric vehicles weight reduction and a zero emissions future mobility. Okay, now we will be starting the event this morning with a welcome presentation and let's say some general information about how the event will proceed today. After that, we will have a keynote session, and I will be giving you an overview of the general results we've obtained in the Fatigue4Light project. After that, a very short coffee break, and we will continue with the technical session, in which several partners from our consortium will disseminate with you some very interesting developments we have achieved during these past 3 years of work in our consortium. This session will continue, let's say, until we will have another small break, and we will end the event today with a round table. Okay, where we have industry experts in our consortium who will be openly discussing future perspectives for lightweight and advanced high-strength steel materials and components applied to the automotive sector. We expect to be closing the event at about 1 o'clock, more or less, and we kindly ask you to add any questions that you may have for us, for any of the speakers today. Please ask your questions by chat. But how do you get to the chat part? Well, when you connect to our Fatigue4Light final conference, you have access to this room where you have several different options. And one of them is take a look at the communication materials that we've prepared for the project and for the event today. Also, we have been publishing quite a lot in these past 3 years. So you have access to the scientific publications that we've prepared from the consortium with the work that we've been doing. You have access there, so you can click and download them. You have access also to the detailed program for our conference today, if you click the button that you see on my screen. And if you want to follow the conference, so if you want to look at the presentations, hear us, and be able to ask questions, okay, for the speakers today, then you have to click the streaming button and you get to follow the live conference, okay? Okay, some logistics and practical information. As I was saying, we are very keen on finding out, on interacting with you, with your questions, with your doubts, and generating a very nice and fruitful, I hope, discussion. But if you have questions for us, you'll have to ask them by chat. There won't be an option for open mic. So please, in your window where you see the presentation, you have the option to select the speaker that you want to pose the question to and type your question. The moderators for each session will receive your question, and after the technical presentation, we will have a moment where we have a Q&A part planned for each of the 3 sessions in our final conference, okay? So please don't be shy, ask as much as you can. The idea is for us to share with you everything that we've been working on, also to get your perspective and what is your feeling, right, for the usefulness of what we've developed, for how we can continue to pursue this line of work. Maybe how can we collaborate, how can we generate new opportunities in the future, okay? Okay, now I would like to pass the word to Daniel Casellas, to the Scientific Director of EURECAT, so he can introduce our keynote speaker for today. Danny?
Good morning, everyone. Lucia, thanks for the introduction and for the first words about the project. I just would like to say that during these 3 years in the Fatigue4Light, we have been developing lightweight solutions adapted to the specific needs of the chassis parts. These solutions are based on the development of the introduction of developed materials with high fatigue performance, and the development also of experimental and modeling tools to facilitate and to promote the implementation of these solutions in electrical vehicles. Lucia will give you an overview of all these results at 10. In the last years, there were a lot of projects dealing with lightweight in vehicles. Is what we need to reduce CO2 emissions. But I would like to remember that this Fatigue4Light project is one of the first European consortiums that holistically address the reduction of weight in the chassis parts, especially thinking in the needs that electrical vehicles will have. We understand that this is the way to reduce CO2 emissions, of course, and also to extend the range of electrical vehicles and boost their introduction in the European roads. If we think about the CO2 emissions effects, in the coming years, the vehicles that will have a higher increase in the CO2 emissions are the heavy-duty vehicles. And also heavy-duty vehicles needs to consider fatigue resistance when designing most of the chassis parts. So we think that the perfect talk to start with this conference, final conference for the Fatigue4Light project, is about what is going to happen in the heavy-duty vehicles. So it is a pleasure for me to introduce our invited speaker, Henrik Sieurin, that he will talk about the fatigue and sustainability of electrified heavy-duty vehicles in the coming half an hour. So Henrik is, just let me introduce briefly a CV from Henrik. Henrik is an expert engineer at Scania in Sweden. He has a PhD in material science from the Royal Institute of Technology in Stockholm. In the last 10 years, he has been at the Scania Materials Technology, working with the structural steels for truck and buses. And Henrik is one of the persons that controls or knows a lot of things about materials and fatigue in trucks. He also has previous experience working with steel-related issues, especially failure analysis, corrosion, mechanical testing, and welding for the offshore and the energy industry. So again, Henrik, thanks for accepting the invitation to give us a keynote lecture. And please go ahead. You have half an hour to explain your thoughts and insights about the application of lightweight solutions in heavy-duty vehicles.
Okay, thank you very much for the kind introduction, Daniel. Henrik Sieurin is my name, working at Scania Materials Technology. And as already mentioned, I will say a few words about fatigue and sustainability of electrified heavy-duty vehicles. And in the picture, you see our latest fully electric truck with a driving range of 4 hours, which is what is required, because after 4 hours, you need to take a 45 minutes break, at least in Europe. And during that time, it's possible to recharge for another 4 hours driving. So this is an overview of my 30 minutes. I will say just a few words about Scania and then what kind of materials that are used in the truck. And then I will focus on, obviously, on fatigue properties, especially for trimmed edges and punched holes that we have been focusing a lot on recent years. And in the end, I will also say a few words about a life cycle assessment study that we have been doing, comparing a combustion engine and a battery electric truck. So Scania, we produce trucks, everything from long haulage, construction, and distribution. We also, due to our modular system, we are well prepared for building more special purpose vehicles like fire trucks, for an example. We also produce buses and engines for marine applications or gensets, and of course, network and services related to our hardware and also used vehicles. So Scania is a relatively old company, founded in 1891. We are about 57,000 employees in over 100 countries. Last year, we spent about 1 billion euro on R&D. And we are also very proud of that we have been doing profit since 1934, which is some kind of record, I think. Scania belongs to the Volkswagen network, and you see the 13 different brands within the Volkswagen group. And this is, of course, very nice to have this internal network when you work with R&D to share experience and knowledge. But in the heavy duty vehicles section of the Volkswagen group, a company called Traton is created, where you find the heavy duty vehicles. So we have Scania and MAN, we have Navistar in US, and we have Volkswagen Omnibus in South America. And we are working very heavily on finding synergies, obviously, to have a common platform both for chassis and cab, just as you see for passenger cars in the Volkswagen group, for an example. And to start with, we are now focusing on finding common platforms for Scania and MAN that you might say might be the most similar vehicles, and then we will continue to also work more focused on common cab and chassis for the other two brands. So the modular system is really one of the key factors for our success. So we have a limited amount of part numbers with a few fixed interfaces, and by this you can combine and tailor suit the truck for every customer. Generally speaking, every customer's truck are tailor suited for their business, so to say. Scania was the first heavy-duty vehicle manufacturer that in 2020 committed to the science-based targets, and this is something that we really are committed to fulfill. In 2025, that's already next year, I realize, we will reduce our CO2 footprint from our own production or operations with 50%, and I believe that is already fulfilled. Then we have to be honest, more challenging part, and that is the scope 3, in other words, the CO2 footprint from our products in service, and this is 90% of our total CO2 footprint. And in order to do that, we have to electrify our vehicles to reduce the tailpipe emissions. And we are on a good way. As I showed in the first picture, we now have a truck, a 40-ton truck that can drive for 4 hours. For the most heavy transport, 60-ton, we are not really at 4 hours, but pretty close. For many customers, 3 hours is good enough. But the next step will be to also reach 4 hours for the most heavy transports. And by 2030, we expect that 50% of our sold trucks will be electrified. So enough of Scania background. I will now focus more on steel and fatigue, my favorite subjects, and especially then structural steel or steel sheet metal. We have first we have the cab that looks from a material point of view, similar to a passenger car with similar requirements, similar material grades. And then we have the thicker sheet materials for the chassis components. So for the chassis, we have typically between 3 and 10 millimeter thick steel, thermomechanical rolled in general, but also press hardened steel for crash resistance, like a front underarm protection and bumper here. And you might also see more press hardening steels for the battery electric vehicles. This is a traditional combustion engine chassis. And the requirements are, well, I would say that fatigue is the most important property that a chassis is dimensioned for, but of course you also have stiffness, corrosion issues. The cab, on the other hand, is another world. Here we have cold rolled steel and similar grades as you found in the passenger car. It's DP steels, CP steels, microalloyed steels, and also press hardening steels, galvanized, of course. And here the requirements are more crash, stiffness as well, surface finish, and of course you have fatigue requirements also for the cab. So when we now electrify our tracks, we front new challenges due to mainly the size and the weight of the batteries. We will have to load many tons of batteries in order to get them a good range. And the batteries are, they are big. So we have a limited amount of space. So we need to have high strength, very formable steels in order to optimize the design. And as mentioned, they are also heavy, these batteries. So in order to still have some load carrying capacity, we need to of course reduce the weight. Lightweighting is very important. I would say even more important. And the batteries are also expensive, so we have to find also cost sustainable materials. Steel are still relatively cheap compared to other lightweight materials. And the batteries are sensitive. We need good crash protection, and that also asks for advanced high strength steels to do this job. So outlook. So I mean, there will be an increased demand for fatigue and high strength steels with state-of-the-art forming technologies for the electrification journey. And again, the requirements, we have fatigue and we have crash. And I will focus on fatigue in the coming slides, but crash is also important, obviously, and not only protect the truck driver, but also protect the driver in a passenger car in case of a crash. And the way you do for designing for fatigue is that first we drive a truck on our test track with different obstacles, simulating real road conditions. And then we take these signals and move them into a shake rig where we can accelerate the fatigue testing in a more controlled atmosphere. And of course, we also have a digital model for the design and calculation engineers to find the hotspots and find where we need to maybe reinforce the structure or redesign in order to have good enough strength. And when I put together these slides yesterday, the previous slide I have showed many times before, but I realized that I thought that there was something missing here. And that is the material part. Because when the design engineer or calculation engineer comes to us in the materials department, they ask for material data, quite often rather specific material data. It's not enough to do fatigue testing on a polished sample, but they need to know what fatigue properties do we have in a bend with residual stresses, or in a punched edge, or a trimmed edge. So this is obviously also one piece of the puzzle, I would say. And then I will move on then to focus more on fatigue. And as you are aware of, we don't have a linear relationship between the yield strength and the fatigue strength. It depends on the surface roughness. So if you have a relatively smooth machined specimen, for an example, well, there is almost a linear relationship. Increased yield strength give increased fatigue strength. But in a component, like a sheet component, the surface roughness is, for a punched hole, we might be somewhere between 20 and 30 RZ value, and for a trimmed edge, it might even be between 30 and 40. And then you have this brown or blue line here. So as you see, increasing the yield strength, increase the fatigue strength up to about 600 in yield. But then it's make no sense increasing material strength anymore. So this is, I mean, how we have thought in the past, maybe. But of course, if you still want to increase the fatigue strength, what do you do then? Either you have to work with the surface roughness, or you can introduce compressive residual stresses, or even choose a material with a lower notch sensitivity. So working with the material, well, different microstructures, first of all, generate different surface roughness if you machine it, if you punch it, for an example. A ferritic perlitic material gives generally a rather rough surface with a bad surface roughness. On the other hand, if you have a pure martensitic steel, you get more like a cleavage fracture with a better surface roughness. And then also the notch sensitivity actually depends on the microstructure. I have learned that the crack propagation is independent of the material strength, more or less, but that's not totally true for these more advanced high-strength steels with complex microstructures. The microstructure do matter, and I will talk more about that later. And of course, you can also introduce residual stresses, and that also depends obviously on the strength of the material, but could also depend on the microstructure. Another way to do this is to work with the manufacturing methods. Laser cutting, for an example, gives a much cleaner surface with better roughness, and you might even introduce compressive residual stresses at the same time. So this is another way to avoid and you can also introduce mechanical surface treatment like shot blasting or peening. And this has a combined effect. First, you introduce compressive residual stresses, but you can also improve the surface roughness and the round corners and so on. So I have a few examples. Example one, two-step punching. In the side member, you have a huge amount of holes. And from these holes, fatigue cracks can initiate, especially if you have an empty hole close to a bracket, like you see in the picture. So when you punch a hole, you get a shearing zone, a fracture zone with a relatively bad surface roughness, and here fatigue cracks can initiate. But if you do the two-step punching, then you first punch a smaller hole with a smaller diameter, and then you come after with a slightly wider punch to shave off a piece around the edge. And by doing this, you get much nicer surface. So to the left, you see a typical one-stage punched hole with the shearing zone and the fracture zone. You see quite high hardness in combination with the poor roughness, which is not good for fatigue. In the two-stage cutting or punching, on the other hand, you can compare this blank zone, this shearing zone. It's much longer. You have no residual stresses, and you just have a small fracture zone. In this project, we did obviously fatigue testing then of punched holes, comparing the traditional one-step punching and the two-step punching. And this is the results for the 700 MC material. So as you can see, the fatigue strength, I would say, mention also that it's generally for a track chassis, it's around 100,000 cycle that we dimension for. So at this value, we increase the fatigue strength with about 100 megapascals. That's 28%. So that's, I would say, is a huge increase by a relatively simple method. And for the 960 material, we see a similar increase. So this is a good way to increase the fatigue strength in punched holes. I move on to an example of how the microstructure also can influence the fatigue properties in a punched hole. So in this study, we compared 3 different materials. We had a complex phase steel, we had a ferritic material with precipitates, and then we have a ferritic perlitic material. And the yield strength was rather similar for these 3 grades. The complex phase had the lowest yield strength. The ductility, elongation was also rather similar. The complex phase actually had the lowest ductility, and the surface roughness was also rather similar. The complex phase actually had the poorest roughness in this fracture zone. And despite having the lowest yield strength, lowest ductility, the poorest surface, it had the highest fatigue strength, 380 compared to 320. So that's almost 20% better fatigue properties, despite these other factors that you would assume would give a lower fatigue strength. So one reason for this, or we try to understand why, we did fracture toughness testing performed at EURECAT with this essential work of fracture method. And as you can see, this complex phase steel had almost a doubled fracture toughness compared to the other materials. So that indicates a better or a lower crack propagation rate. So here we come into this notch sensitivity, because in a punched hole, you always have crack initiation. You already have micro cracks. So it's really about the crack propagation. And then I know that a Catalan institute that have been working quite a lot to try to relate this fracture toughness to the fatigue properties, which is very, very interesting for designing new hot-rolled advanced high-strength steels for good fatigue properties. And this work also motivated us to start a PhD project at KTH, which is done by Nader Heshmati, and And he tried to dig deeper into this and understand how the microstructure influence the fatigue properties of advanced high-strength steels. So in his work, he has been using the 500 MC, which is the most common steel used in the chassis, and 3 more high-strength materials with similar yield strength, but different microstructures. And in his work, he found that this 700 MC plus material actually showed a much lower crack propagation rate compared to the other materials. And it also showed better fatigue properties, even in a punched hole compared to the other materials. And he has really digged deep into, studied how the crack propagates in the microstructures, and tried to describe these differences. And there are mainly 2 reasons that he has found. First, we have, well, if you look at the crack propagation in this material, we have a combination of transgranular and intergranular crack propagation. So the crack propagates transgranular with grains with a low Taylor factor, and then it starts to grow intergranular in grains with a higher Taylor factor. And in addition to this, this material also have martensite on the grain boundaries. So there the crack has to, again, propagate intergranular also around this martensite on the grain boundaries. So I had hoped that now they would give me a simple explanation to how the microstructure influence fatigue, but unfortunately he just made everything even more complicated for me. So now we also have the influence of the texture. But yeah, the more you learn, the more questions you get. That's fantastic. There will be more things to do, fortunately. And then I continue with another example of how to increase the fatigue strength in a chassis component, and that is by this mechanical surface treatment. These 2 pictures show the influence of a simple shot blasting. Shot blasting is mainly done to increase the corrosion protection, to improve the painting, to get rid of oxides, scales, and so on. But as you see, it also have a really positive influence on the fatigue strength. So to the left, we compare 355, 500, and 700 MC material at 100,000 cycles. 355 is worse, but the 500 and 700 is similar. But with shot blasting, the 355 material, there is not a really big difference. This is a relatively soft material. But for the 500 MC, the fatigue strength increase with, well, from 370 up to 450. And the 700 MC, we go from 400 up to 600 megapascals in fatigue strength. So this is obviously also make a big difference. Then it also depends on how the material is loaded. You have either you can load the material as shown in the picture above here on what we call the low edge, where it's the rolled surface that are loaded, or you can have the material on high edge where the whole edge is loaded, so to say. If you have a not shot blasted material, for these high edge loading, we see no influence of there's no point increasing the yield strength. It's the same. For the low edge, well, there is a slight increase. But if we introduce shot blasting, on the other hand, for the low edge bending, we have a almost linear increase in fatigue with the yield strength, and even for the high end specimen, the influence of the shot blasting is really great. Okay, I will continue with the last part of my speech, and that is LCA. An LCA analysis that we did a couple of years ago that I think is quite interesting. And in this study, we compared diesel track and ICE with the battery electric track. They had the same configuration, the same load, and we assumed 500,000 kilometer life length with an average payload of 6 tons. And this BEV, this was our first generation BEV with a slightly lower amount of batteries compared to what we have today. Today we have the double amount of batteries. But anyhow, first we'll look at the bill of materials. For a diesel truck, we have more than 50% steel. We have quite a lot of cast iron and then some other materials. The difference for the battery electric truck is that we introduce batteries that is quite a lot of weight. This is, as I said, a limited amount of batteries, 300 kilowatt hours, I think. So these will double more or less if we look at our latest truck. Steel is still around 50% of the weight of the battery electric truck. And then if we look at the greenhouse gas emissions from the vehicle production, we see that for the diesel truck, almost 50% of the emissions from the production comes from the steel production. On the other hand, if we go to the BEV, we see that now it's the battery production that generates the highest amount of CO2 footprint. And this is due to the cathode and anode production, which is done, well, in the past with a relatively bad energy mix. Of course, you can reduce this if you use wind energy or some pure energy. And steel is number 2. So we can then take a look at the potential with the BEV compared to the diesel truck. In a diesel truck, the CO2 footprint comes from the use phase, and that is more or less what comes out from the exhaust pipe, and that is the major part, more than 90%. And then we have smaller part from the production and some other things. If you then shift to a BEV, there comes out nothing from the exhaust pipe, but now it's the well to tank, that is the energy production that generates the highest emissions. But if you then go to better electricity mix, for an example, what is assessed for the EU energy mix in 2030, the amount of green electricity increase all the time, and by then this part has halved. But what happens when you go to the BEV is that the production part increases, and this is due to mainly to the battery production. But if we then assume that we have pure wind energy, for an example, then we have this use phase has now decreased radically. And now the biggest part is actually the production part. And here is where we have the battery and steel production. So in order to increase even more, to come close to 100% reduction, we need to work with this part. We need green electricity for the battery production. Scania are now purchasing our batteries from Northvolt that are using green electricity. And then we have this fossil-free steel that will come in a few years that will also help us to decrease this part so that we get close to zero here. And we have quite ambitious requirements for our supply chain when it comes to this. We have these 4 areas that we focus on. It's battery, steel, aluminium, and cast iron. And we have requirements for how we define green steel and how we define green electricity. And from last year, we have now requirements on our suppliers that they shall at least have a plan for how they will decarbonize their production. So finally, concluding this LCA part with sustainable battery production, fossil-free steel, and green electricity, there is potential for BEV trucks to decrease the CO2 footprint by well more than 90%. And also that the load carrying capacity and battery protection of BEV will put even higher demands on high strength steels with good fatigue and crash properties. And the demand for these materials will continue to grow. And this is a very interesting area to work in. I think you all agree with me. Okay, that was my last slide. And I see that it's 10 o'clock, so good timing, I suppose. Thank you very much, everyone.
Okay, so we've had a super interesting lecture from our keynote speaker, from Henrik. Thank you so much. And now it's my turn to share with you a bit of a general overview of our project, of the Fatigue4Light project that is, let's say, the organizer for the conference today. Now, ideally, if you are here, probably this is not the first time that you're hearing about the Fatigue4Light project. But just in case there's somebody who found out about us just some days ago, let me just say that Fatigue4Light stands for fatigue modeling and fast testing methodologies to optimize part design, and also we want to boost lightweight material deployment in chassis parts. Okay, so this is a very interesting point. So we have like keywords, main keywords for our project. Obviously, good fatigue performance, lighter materials, and we are targeting chassis application. Okay, now my purpose today is to give you an overview of some data about our project, of our consortium, some project phases that we've been going through in these past 3 years. Let's speak about new materials that we've analyzed and we've studied in the Fatigue4Light consortium. And after that, I will give you an overview of the results that we have obtained in the project. I won't spend too much time here, but there are some very interesting lectures that are following this session that will get into more detail on different perspectives that we've been pursuing in the project. So just a global vision, let's say. Who are we? Who is the Fatigue4Light project? What is the Fatigue4Light project? Okay. Well, we are a Horizon 2020 project. We started working 3 years ago. We are funded obviously by the European Commission under the Horizon 2020 program. And the budget for our consortium was 5 million euros. And we are quite a varied consortium. We are 13 partners joining from 4 different European countries. The coordinator of the consortium is CIMNE, CIMNE stands for International Center for Numerical Methods in Engineering. This is the research center where I'm working. I've been working for the past 14 years, I would say. And our expertise, our specialty is, of course, numerical simulation. Okay, now in the consortium, we have a very interesting mix, I would say, of capabilities and of different perspectives, because we are 3 research institutions. We have 3 universities which have joined us, but the biggest weight in our consortium is taken by the industrial companies. So we are very happy to have been able to collaborate with all of these industrial partners in the past 3 years. And today you will have the opportunity to hear their perspective on the lightweighting process that we've been pursuing in these past 3 years, and also perspectives for the future, because we've been working hard these past 3 years, but we don't want to stop here. Obviously, the idea is to use as much of the developments that we have reached in the project, use them for the future, right? To take them even further. Of course, we've developed some interesting stuff in the project, such as some new experimental techniques. And when you are dealing with new experimental techniques, you need standardization, okay? You need a standardization process to be able to make these techniques, to take them as close as possible to other users who might be interested in using them, of course. Okay. Now, who are we? Because today we are seeing each other in this virtual format. I think you can see my face, but the work that I will be showing today and the results that I will be sharing with you, they are the result of the work of many people. So we are, as I said, quite a big consortium. We started 3 years ago, of course, with the pandemic still raging its effects. So we've had several meetings, unfortunately, in this virtual format, but little by little we migrated to this online, from the online version, let's say, to the in-person gatherings. And here you can see the evolution that we've been throughout the years. Okay, so we've gotten a lot smarter, probably with some more white hairs, but we are very happy to have made it here today to be able to share with you all the knowledge that we have gathered. And just a more recent picture of us. This is us at the last consortium meeting that we organized, I believe, about 10 days ago here in Barcelona, in Spain. Okay, now let's get into the Fatigue4Light project. In our work plan, what have we been working on in these past 3 years? You see, we started with a first year, which was very focused on material development. Okay, so we chose different materials in our project, and we had an intense testing campaign at coupon level to see how they performed under different types of tests. Okay, after that, after, I would say, at the same time, a different team was involved on proposing some fast experimental techniques for fatigue, because, as you know, I hope you know this, fatigue is quite costly from the point of view both time-wise and cost-wise, because it requires quite a large amount of experimental tests to be able to have properly characterized a material. So we've spent some time to promote, to develop these new experimental techniques very fast. At the same time, a different team was involved in developing computer and simulation methods, because we were interested also in proposing some advanced numerical techniques to be able to model fatigue, but also to model the influence of the manufacturing processes on the fatigue behavior, because, as Henrik has said, the manufacturing processes, they are crucial when you're trying to evaluate the performance of different components, chassis components that have passed through different processes. They will clearly have an influence. So we were focused on, from this both the experimental and the numerical perspective, we focused quite a lot of effort on understanding how the manufacturing processes later on affected the fatigue performance. And all of these work culminated, I would say, in the third year, when we spent some time and a lot of work working on at component level on validating all of the different techniques that we have developed in the project at demonstrator level. Okay, now I said that we have been studying different materials in the Fatigue4Light project. Here you can have an overview of what these materials were. On the one hand, we were focused on studying the behavior of advanced high-strength steel. So we had complex phase 800 and complex phase 1000. 800 for applications where this material was not the current state of the art. And CP1000 for materials where the state of the art was CP800, and it was the component, let's say, was selected for an improvement process, a lightweighting process by changing its material. Okay, after that, we had some material solutions that targeted hybrid materials and stainless steel. And when I speak about hybrid materials, what I'm referring to is our metal composite sandwiches, okay, where we had some outer layers made with aluminum and an inner core of glass fiber reinforced polymer. Okay, we also studied martensitic stainless steels adapted for press hardening. Another material, now that I've mentioned press hardened, another material that we studied in the project specifically for heavy-duty applications was the 22 manganese boron 5, the advanced bonus steel. And as I said, we also targeted aluminum alloys, which had improved fatigue resistance, reduced cost, and also they had an improved environmental profile because they incorporated a high amount of scrap in their composition. Okay. Now let's get to the results part, and here I have to go fast, so you will get this bird's view right from above. But if you have questions, the lectures that will come after on, they will focus specifically on different aspects of these results, and feel free to ask us whatever you need. So in the first year, the experimental campaign, coupon level. We wanted to check the performance of these different materials that we analyzed in the project, obviously from the tensile point of view through tensile test, studying their local formability with the hole expansion test. Of course, we were interested in the fracture toughness and some environmental effects that were studied by means of the corrosion test. And here I'm just giving you an overview of how the different materials compare for different types of tests. But as I said, later on, you will get more details. Okay, now the most important test, I would say, that for us, for the consortium, was of course the fatigue performance of these different materials. And in this sense, the fatigue experimental campaign that we developed in the first year was focused on 3 different techniques, well, 4, but I would say one is the conventional staircase method that everybody knows, I'm sure, that is widely used. And it was our comparison point to see how the techniques, the experimental techniques that we developed in the project were comparing to it. After that, we started to develop and to look at the results for some fast experimental techniques, which were based on different concepts. One of them was the self-heating method. This was proposed by our consortium partners, by our colleagues at ArcelorMittal. After that, a different fast experimental technique was the stiffness method developed by our colleagues at Eurecat. And we had an experimental campaign which was focused also on very high cycle fatigue, so by ultrasound testing, which was developed by our colleagues at Politecnico di Torino. What you can see here and what I will show you is an overview of how the different materials ranked in terms of their fatigue limit normalized by their weight, okay? So we can compare more or less the performance of the different materials. But if you are interested in specifically these fast experimental techniques, which I believe they are very useful, okay, for people that are working on the experimental part of fatigue, you will have a talk in the next technical session given by our colleague Sergi Parareda from Eurecat, and you can find out more specifically about the stiffness method developed in the consortium. Also, remember that we have published quite a lot. You can find information in the scientific publications that you can download in the conference hall. Okay, now Second year of the project. This was the year where we went, we took the complexity a little bit further on. So we spent time at a lab scale demonstrator level. And what do I mean with this? Well, we designed this L-shaped profile where we wanted to check how the different manufacturing techniques, such as trimming, such as punching and cutting, were affecting the performance of the fatigue life, the fatigue behavior. And in this sense, we designed two different specimens. One was completely polished, and another one had some areas of the specimen which were left unpolished. And our colleagues at EURECAT did an intensive experimental campaign where, under reversion factor of -1, they tested these lab scales samples. And here you can see just an image of the different failure modes that were observed experimentally, and also an image from the numerical campaign that CIMNE performed on these specimens, because our ambition was, with the fatigue numerical formulation that we have developed, to capture correctly the fatigue life, okay, the number of cycles until failure, but also to capture correctly the crack propagation. So not only the initiation under the cyclic loading, but also how this crack progressed. And you can see here also just a small simulation of crack propagation. Again, more details about numerical simulation later on in the technical session. Now, let's get to the uppermost level, okay, the most complex level. So demonstrator level. In the project, we've studied several demonstrators with different material solutions. So here you have a view of some of them that were built. These are not all. But for instance, you can see the lower control arm that we built in the project in a steel solution from with complex phase 980, complex phase 1000. Also, a version of this lower control arm, which was built with the hybrid solution, aluminum alloy with glass fiber reinforced polymer core. Then we did a very intensive campaign of studying both experimentally and numerically the wheel behavior, both on the disc and on the rim. And we finished with a demonstrator that came from the heavy-duty vehicle ambit, let's say, the cross-beam member. And here you can see the view of the manufactured demonstrators. Okay, now let's focus just a little bit, very fast, on each one of these demonstrators. The steel lower control arm. This was a demonstrator proposed by Fiat, by CRF, our partner in the consortium. And here you can see a view of the demonstrator, which is screwed to the test bench. And we did several experimental tests on this demonstrator to be able to understand the way it behaved. First, of course, a monotonic test, so misuse test. And you can see here, for instance, the failed specimen under this misused test. Also, from the numerical simulation part, we also try to give an answer to these different types of behaviors that were observed experimentally. And after that, we passed, of course, to the fatigue test. And there were several fatigue tests that were done on this component. Here, I'm just showing you an image of one of the failures that were observed on the still lower control arm, where a very interesting mode of failure was observed with the primary crack and then the development of a secondary crack that finally completely broke the specimen. Later on, you will see how, from the numerical point of view, we managed to capture this crack propagation. Okay, let's go to the next demonstrator. So our colleagues at RISE Research Institute of Sweden, they developed, they built, they tested, they analyzed this hybrid aluminum GFRP lower control arm. You can see here an image of the component which is screwed to the test bench. And afterwards, an image of the failed component, and also just a short animation of a digital image correlation test. Okay, from the numerical perspective, of course, we built models for this, we analyzed it, and later on you will see the performance that we got from the numerical point of view. Now, I want to go to a very nice video, which is was done by our colleagues at RISE. Which details the manufacturing of this hybrid lower control arm. And here, if you have any questions, please write in the chat, okay, for our colleagues. They will be able to assist you with any doubts that you might have. From my point of view, just to say that before manufacturing the specimen, of course, we had, let me just lower the volume a little bit. we had to do also a numerical analysis beforehand to identify the hotspots in the geometry, to identify the feasibility of manufacturing, etc. And here you can take a look at the whole process of stamping and joining the different parts. And the final build version. Okay, let's go further. Some other demonstrators, intense experimental campaign, a lot of work done by our colleagues at Magneto Wheels on a wheel prototype, okay, on a disc proto. And here they've been studying different materials and they designed a specific stamping cycle, okay, for the wheel. And they observed some quite interesting stuff. For instance, some materials behave better after the stamping cycle. With regards to fatigue, some materials behave badly, or not badly, but poorer, I would say. Okay. Then, from the numerical perspective, of course, we wanted to give also a response to the behavior observed experimentally. And you will see later on how this compares experimentally and numerically for this specific component. Okay, the last component in the project that I want to show with you today is the cross-member beam proposed by our colleagues at Gestamp. They proposed to us a symmetrical design, so they built only half of the cross-member beam. And you can see here a very nice animation where you can see how the actual manufacturing process is done. It's quite short, okay, so we won't be taking too long, but it's really a beautiful video. Okay. And then you get the end result, which is the cross-member beam, half of it that you can see here, screwed to the test bench and analyzed for different types of fatigue loading in different directions, okay? Here, just a comparison between experimental and numerical, but again, it's not my purpose to spend a lot of time on this part. Okay, so we've tested, we've analyzed at different levels the performance of different materials on different components. Did we manage to reduce the weight? Well, this is, let's say, the overview specifically regarding weight reduction, okay? So only considering weight reduction when changing the material to the proposed material solutions in the project. So for the lower control arm, when we switched to the CP980, we observed that we were able to achieve a weight reduction of about 12% without any performance loss, 20% if we also incorporate design optimization. The hybrid solution for the lower control arm, of course, a high weight reduction, 35%. For the wheel, for the CP800 solution for the disc and the rim, 5% average weight reduction. When you also improve the performance of the material by using a shot peening process on the disc, you get a weight reduction of about 9%. And for the cross-member beam, when we used the press-hardened steel, we observed a reduction in the weight of about 43%, which actually shows you the really great potential of this material to be used on heavy-duty vehicles. But I don't want to leave you only with this perspective of weight reduction. This is not the only important thing when you consider the performance of the different materials today with respect to CO2 emission, with respect to end-of-life considerants, so recyclability, etc. Later on, in the talk of my colleagues, Violeta and Marga from Eurecat and from RISE, you will find out more about the eco-design methodology that we followed in the project and that takes into account several different aspects that might influence what you see here regarding the weight reduction. Okay, nothing more from my side. Thank you very much for your attention. Now we pass to a short Q&A session if you have any questions for us, and if not, later on we can continue to answer any doubt that you might have. Thank you very much for your attention.
Yes, thanks, Henrik, for this very interesting keynote from the shaking cap, from the shaking track to the propagation of a crack into the microstructure. This is what makes material science very exciting, that we can solve big things with a very, very small approaches. Also, Lucia, thanks for the overview of the Fatigue4Light. We will hear more about results in the coming minutes. Now we only have time for a short question. What I will do, Henrik, I put together some of the questions we get from the chat, try to make it only in one. There are some questions about the the lightweight potential of steels, you mostly talk about high strength steels, and it will be enough, the properties we will get from steels to fully reach a completely lightweight solution for a vehicle? Or do you think we will also need the use of multi-material, like some patches for reinforcing crash in the battery section or in the chassis? And to make it a little bit more, shaking more the cocktail, is how these new steels, the coming, call it green steels or steels with a lot of amount of scrap contribution, how this will impact on the fatigue, how you will, as a designing engineers, consider the new steels with maybe more variability and so on. I think I put more or less the questions in a simple one, large one, but Henrik.
Yeah, thank you very much. It was a pleasure to have the opportunity to present for all of you. Well, first of all, let's see, the mixed materials. Of course, I mean, in order to fully optimize the weight and the component, I think that the opportunity to use mix different kind of materials can for sure be a solution, and not at least for crash systems, for an example, where you see different solutions with combining, for an example, an extruded aluminium profile inside a press-hardened profile and things like this, in order to really optimize the properties. That's for sure. And I also believe that this electrification journey, we are in the beginning of it, and there will be for sure room for further optimization of the material selection in the future to increase the load carrying capacity and reduce the weight. But of course, I'm a steel guy, so I like steel, but I don't dislike other materials, and I think that mixing materials can quite often be the optimal solution, I'm sure. And when it comes to the fossil-free steels, I mean, I don't expect any big differences in the material properties, and that's also what the steel suppliers tell us, that we shall not see any big difference. And I'm not really deeply. I haven't really investigated these fossil-free steels in detail. They are not really available yet, but of course you could maybe expect some minor differences in impurities that might influence weldability or formability, maybe, but I don't expect to see any big difference in fatigue properties, for an example. Let's hope for even better properties, but let's see.
Let's go for even better properties. No, thank you. Of course, if somebody else, I mean, the questions we don't have time to do it on live. Please, we can contact the chat, and we can put in contact with Henrik if you want. Thanks again. I think that let's conclude this first block of presentation is that this is not going to be a boring stuff in the coming years regarding lightweight and vehicles and steel development and materials development. So Henrik, if you don't mind, maybe in 5 years we will invite you again, maybe presentially, and see how these slides are changing in time.
I would be happy. Yeah, thank you. Looking forward to the invitation. I will check my emails.
It's on the agenda. It's not. Perfect. No, let's go for a small coffee break, or just setting up everything for the next session. I think, Lucia, we met at, maybe we are ahead of the hand right now, but maybe we meet in 10:30.
I think so, yes. With a short 5-minute break, we have enough.
Perfect. Enjoy the coffee.